Hi everybody, welcome back to chemistry. This is AP Chemistry Chapter 11. This is video number 8. And today we're going to be talking and learning about osmotic pressure. And so I figured I'd define it for you first and then show you a couple examples of it through another video on YouTube. So what osmosis is the flow of water. Water will always flow into a solution, and it flows through a semi-permeable membrane. If it's semi-permeable, that means it only allows certain things to pass the membrane. Think of it like border patrol on your borders, right? You only allow certain people to enter the country. So the semi-permeable membrane only allows certain chemicals to enter into the cell or out of the cell. Typically water can move through a semi-permeable membrane, but larger molecules like sugar and salt cannot move through a semi-permeable membrane. So the flow of water through this membrane is known as osmosis. If you want to stop that flow of water, we call that osmotic pressure. Okay. So osmotic pressure is the pressure needed to stop osmosis. This little diagram kind of shows you what's happening. The yellow mark here, which is in the center of your diagram right here, that's your semi-permeable membrane. Over here, God bless you, we have just water. Over here we might have a solution. Say we have aqueous salt water. Okay? In an attempt to equalize the concentration, so this has a high concentration of salt. It doesn't even matter what it is. Let's say it's 1 molar. But if it's just water, then the concentration of salt is 0 molar. So in an attempt to equalize the concentrations, because again, remember, things in nature want to be equal, water will flow from the pure solvent and enter the solution to dilute it, right? It attempts to dilute the solution. So you can see here then that the water level rises inside the solution side of the tube, because water enters in an attempt to equalize the concentrations. Again, they'll never really be equal, but that water entering will dilute and lower the concentration. Oh, it was salt, not sugar, right? And the reason there's a decreased concentration is because now it's more dilute. There's more water. Okay? But still, it's going to be greater than 0. That will continue to happen. That water will completely leave this side and enter this side unless we stop it. And the pressure we need to stop it, we could apply pressure to the surface to stop the flow of water, is known as osmotic pressure. We can actually calculate that pressure by this equation, okay, where this, it's not pi, okay? It's referred to as pi, but it isn't 3.14 pi. It is the pressure. And it's measured in ATM. So if you want to replace it with P equals mRTI, you may. It's exactly the same thing. M is the molarity of your concentration, of your solution, excuse me. And that's going to be measured in moles per liter. R is a constant that you'll be using. It's a 0.08206 liter atmospheres per K mole. Okay? So that is a constant. It will always be that value. T is your temperature in Kelvin. And of course, I is your Van 't Hoff factor. It's the number of particles that your solute dissociates into. And I know there were some questions about that. So I is the number of particles your solute dissociates into. And remember that covalent things, large organic biomolecules, that I is 1. You don't have to worry about that. This is important in biology, and I want to show you why it's important in biology. So let me show you this little video. From YouTube. I want to give this person credit, so I'm going to leave that on.
Solution versus a hypertonic solution. A hypertonic solution is simply a solution that has a lower concentration of solutes, dissolved substances, compared to the inside environment of a cell. For example, water is considered a hypotonic solution since it is very low in solutes. A hypertonic solution is a solution that has a higher concentration of solutes compared to the cell's inside environment. For example, water with a lot of salts is considered a hypertonic solution since it is very high in solutes. How can we examine the effects of a hypertonic solution on a cell? You might be thinking, well, I'm made out of 50 to 70 trillion cells. If I drink this, I'll know what happens to cells in a hypertonic solution. But do not do that. Drinking salt water can be very dangerous as it severely dehydrates you. Nausea, vomiting, and even hallucinations are just a few symptoms of excessive amounts of salt water. Ask anyone who's been stranded to conduct your test. Are surrounded by a hard outer membrane, which protects the semi-permeable inner membrane. This membrane is semi-permeable because it allows substances to leave and some substances to enter. In particular, the semi-permeable membrane allows water to both enter and leave the cell, but large molecules, like salt or sugar, are too big to pass through. The question is, how can we examine the semi-permeable qualities of this inner membrane with the hard eggshell in the way? Dissolve the outer shell by placing an egg in vinegar. Vinegar has a chemical called acetic acid. Eggshells contain calcium carbonate. When calcium carbonate in the eggshell comes in contact with acetic acid, a chemical reaction occurs. Calcium carbonate will break down to form carbon dioxide, water, and calcium acetate, thus dissolving the calcium carbonate shell. Within seconds, you'll see bubbles form. These bubbles are carbon dioxide that are produced when acetic acid breaks down the eggshell. Within 3 days, you should have a semi-permeable membrane, free of the hard outer shell, to conduct your experiment. Before starting our experiment, we will first mass our egg using a scale. Egg A has a mass of 94 grams. Egg B has a mass of 103 grams. Egg A we will place in a hypotonic solution, water. Egg B we will place in a hypertonic solution, thick and sugary corn syrup. Egg A now has a mass of 97 grams. Egg A increased slightly to 103% of its original weight. We can conclude when a semi-permeable cell is in a hypotonic solution, water will enter the cell. Egg B now has a mass of 59 grams. Egg B decreased to 57% of its original weight. We can definitely conclude that when a cell is in a hypertonic solution, water will leave the cell. In fact, this is evident by the layer of water sitting on top of the corn syrup. However, 103% change in mass is not very significant. So how about we try this experiment again, but switch the eggs? This time, egg A is going in the hypertonic solution, which is still on the right. Egg B is going in the hypotonic solution, which is still on the left. After several hours, mash your eggs again. Egg A went from 97 grams to 55 grams. Egg A has decreased to 57% of its original weight. Egg B went from 59 grams to a whopping 105 grams. Egg B has increased in weight to 177%. From this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters a cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically salt water, water will leave the cell. Now that you're done with this experiment, time to play with those shellless eggs. No! You're just gonna...
So the application of this is obviously in your bloodstream with your body and your cells, although it was demonstrated quite well with eggs, and I think we should do that this weekend, is we should dissolve some eggshells and then place our eggs in hyper and hypotonic solutions. But the top picture here shows you what a normal red blood cell looks like. Here you have a shrunken red blood cell, and the reason it would shrink is that it would be surrounded by a solution that is a very high concentration of solute relative to the inside of the red blood cell. So if there's a high concentration on the outside, water will leave the blood cell in an attempt to equalize the concentrations, and so the blood cell shrinks. On the other hand, if you have too low of a concentration compared to the inside of the cell, if it's too low, then water enters the cell in an attempt to dilute, the inside of the cell. Okay? So that's the application of it, and that's why our body is so susceptible to being dehydrated and not having enough ion concentration and things like that. We can actually go into kidney failure because we stop being able to function when our red blood cells break down, and other cells in our body. So osmosis is vitally important in our body. Of course, we always have to quantitate things, so let's try a couple practice problems. What concentration of sodium chloride in water is needed to produce an aqueous solution isotonic with blood? Isotonic means same osmotic pressure. So the osmotic pressure of blood, the pi, if you will, is 7.70 atm. The temperature that we're at is 25 degrees Celsius, which is 298 Kelvin. And they want the concentration of sodium chloride. Remember, concentration is molarity, and sodium chloride is a metal in a nonmetal. So it's ionic. The I equals 2. So if we plug into our osmotic pressure formula and we solve for for our molarity, we have 7.70 equals X times that constant, 0.08206, times our temperature, which is 298, times our I, which is 2. And if we solve for our X in this case, you should get, if you solve for your X equals 0.157 molar. So that is the salt solution that we need to give. And that's applicable because if you're dehydrated and you go get a Ringer's solution or an IV at the hospital, it's going to be this concentration. Because if they make it too low and then your blood cells are bathing in it, you're going to have problems if the concentration's too high. So when you get an IV and it says Ringer's or saline solution, it's going to be this concentration, so it has the same concentration as your blood. Okay, so we're going to pause with this problem and come back in the next video. So you'll have to watch the next video for the conclusion.